So before I just jump into this next example of a washer method, a volume problem, I kind of want to give us a quick test of whether or not we caught in the last lesson that concept of the outer and inner radius. So I'm going to sort of draw a random example here. Suppose that you've got, a function up here, f of x, and then you've got another function here, g of x. And suppose that I'm going to ask you to revolve this around the axis. Let's revolve it around y equals 1. Right? So if I'm going to take this region here and revolve around the line y equals 1, the question that you need to be able to do before we move on to what we're doing in this lesson is, what would an expression be for the outer radius? And what would an expression be for the inner radius? So pause the video, write those down really quickly. They should be quick things to do if you caught that in the last lesson. So for the outer radius, I'll do this in green. I start at the axis of rotation, and I draw past the first function I hit all the way until I get to the other function. And what I want is an expression of what that distance is. Right? This is always supposed to be the top function minus the bottom function. Well, the top function is f of x minus the bottom function is 1. So that's the outer radius. The inner radius I'll do in red. Again, I go from the axis of revolution up until I hit the first function that I find, and that distance is supposed to be my inner radius. So once again, I do the top function, which is the g of x function, minus the axis of revolution, minus the bottom function, which is 1. Right? You're going to need those in order to come up with what the volume of these things are when we're revolving around. I suppose while I'm here, I could sort of ask one other similar question. Suppose we had the exact same setup. You've got this function f, you've got another function g, but this time I want to revolve around a line up here. Suppose I want to revolve around y equals 5. Right? In this case, what's the outer radius? Well, if I go from the axis of revolution past the first function down to the other function, the difference between those two things would be the top function, 5, minus the bottom function, which is, let's see here, this guy here is the g function, so this would be 5 minus g of x. Right. Similarly, the inner radius goes from the axis of revolution to the first function you hit, which this time is the f function. So you'd have 5 minus f of x. So I just really wanted to make sure it was clear what this concept of inside and outside radius is. And just one last time, if this is the region, when I revolve that thing around that, this f of x is going to sort of form the outer edge of the three-dimensional shape that I'm forming, whereas g of x is going to sort of form the inner form of it, and that's why g of x shows up on the inside here and f of x on the outside. When I switched it around here, they switched. Hopefully that's clear. Let's get to the solid example that has real numbers in it. We want to let the region S be bounded by the functions x squared, which is a nice simple parabola, and the function g of x equals x plus 2, so up 2, and from there we're going up 1 over 1. So we've roughly got a graph that looks like this. So the region we're talking about seems pretty clearly to be this section inside here. When you've got a setup like this, it's a good idea to sort of figure out what the points of intersection are, because we know we're going to want to know what these things are in the end, so we might as well figure it out early. When is x squared equal to x plus 2? This should be a simple factoring problem. If we move everything over to one side and factor, I'll get x minus 2, x plus 1. So I got x is 2 and x is negative 1. That matches with what I have here. It looks like this is probably the 2, this is the negative 1. Those seem to fit, and that's great, because now I've sort of already got the third step done. I've got my bounds. So now I can sort of set out to look at the rest of this problem. I'm supposed to revolve this thing around the line y equals negative 1. So I'm revolving it around this line down here. Okay. So step 1 in this process is to identify what the thickness is. Because I'm revolving around a horizontal line, like the x-axis, we know that our thickness is going to be dx. The second step is where we're supposed to identify what the radius is. But because there's this sort of white space in between, we know this is going to be a washer method problem. That means it's going to have an outside radius and it's going to have an inside radius. So we'll look at each of those individually. First, the outer radius. I'll draw from the axis of revolution up until I get to the outer radius. Note, along this line, it really doesn't matter where you pick to draw it. I'm just drawing it so that we can sort of see, hey, it goes from here to here. And so that it makes it easier for us to say, okay, the two things being connected are the line and the axis of revolution. So when I come over here to write down what my outer radius is, I can write, well, it's x plus 2 minus negative 1. And my inner radius, I'll go back with the red marker for this one. I'm going to go from here, the axis of revolution, up to the inside function, to the first function that I hit. So in this case, the top function is x squared minus, and the bottom function is negative 1. And so I suppose we could even, we could sort of go back and pretty those up a little bit. If I simplify the top one, this would be x plus 3. And if I simplify the bottom one, this would be x squared plus 1. And so those are going to be my outside radius and my inside radius. The third thing that we need is we need to identify what the bounds are. Well, we did that earlier. We found the points of intersection were negative 1 and 2. Great. That means that my bounds are going to go from negative 1 to 2. The final thing we need to do is we just need to put all this stuff together and write out what the integral is going to be. We know it's supposed to be pi times the integral of big radius squared minus little radius squared times the thickness. So now that we've set all this stuff up, it's really just a matter of plugging this stuff in. I have pi times the integral from negative 1 to 2 of, and my outer radius was, I'll even color code this for us. It's going to be this x plus 3 squared. Then we have minus, and then I'm going to have my inner radius, which was x squared plus 1 squared. And this is all with respect to x. And that is our integral expression for the volume of revolution. Could this be done by hand? Sure. It just means we're going to have to FOIL this thing, we're going to have to FOIL this thing, we'll subtract them, then we'll integrate, we'll plug in these numbers. It's going to be a somewhat lengthy process to do by hand, and so a lot of times on these problems, they're just going to be looking for, can you set them up? Very commonly, these will be calculator problems, so we'll get some practice with that in the coming days. I suppose an exercise for thought, if you want one more thing to think about, is this idea of, what if I had us revolve around a line up here? Right? Would that change the outer and inner radii? And it should, right? The outer radius from up here would go to the squared function. The inner radius would go down to the line function. Things would be different. But I think if you're able to draw these pictures, and if you're able to clearly label where your axis of revolution is, and if you draw in your outer and inner radii, you kind of can't go wrong if you're careful. So that's all I've got. I'd really recommend you guys take a look at a few of the problems in the assignment. Make sure you've got the hang of it before you get to class tomorrow. So I'll see you then.